So this is going to be inference for a proportion. And let's start with an example. According to a New York Times poll in June 2012, only about 44% of the American population approves of the job the Supreme Court is doing. I should mention this poll was a simple random sample of 976 adults. Okay, so we have the sample that we took and we have a bunch of data, but note that every single person in the sample is just saying yes or no, approve or disapprove, right? And we've sort of boiled all of our data down to this proportion of people who said approve. And I want to make an argument about this value, this sample proportion. And it's that a proportion can be seen as a sample average x bar. So this is a little new. Remember, the sample average is a sample mean. I take all my data, add it up, divide it by n. What I'm saying is there is sort of like an equivalence or a homology between this sample proportion and this sample mean. And the way that we make that connection is if we represent each response that each person that says approves, they approve of the job the Supreme Court is doing, as a 1, and each does not approve as a 0, we'd get that the sample proportion, so the proportion of people that we observe as saying they approve in our sample, as equal to, well, the first person maybe said they disapprove, so I'll encode that as a 0. Maybe the second person said approved, and then another approved, and so on and so forth. Maybe the last person said they didn't approve. Over the total number of respondents, which was 976, and this looks very much like an average. You add up all the points and divide by n, and as you can see, it's equal to our sample proportion, right? So to say that maybe in another way, that is, the sample proportion is equal to 1 over n, the sum of the x values, where each xi is either 0 or 1. Okay? So we are likely going to want to perform inference. That's kind of the next thing I'm going to be pushing us towards. And what does inference mean? It means we have this unknown value associated with our population, and we're going to say what we can about this unknown value with our sample. So in this case, our sample is this p hat, right? And we're going to use it to say something about the population proportion, which is if I could ask every single person in the United States whether or not they approve or disapprove of the Supreme Court, what are the proportion of people that would say approve? It's not really feasible for us to ask every single person in the United States, so we're performing this inference thing. And the thing I'm trying to argue is that inference on a proportion is just like inference on a mean, because really you can view proportion as a mean, because it is. So let me make a few points before we move forward of actually how to do this. Let me remind you that when we show that x bar is normally distributed, we can perform inference. Right? Whenever we were doing hypothesis tests with the sample mean or confidence intervals with the sample mean, we would often check our assumptions so that we could say that x bar was normally distributed, and then we would move forward. I also want you to note that p hat, the sample proportion, just like the sample mean, is itself a random variable. Right? This was the other idea. Different samples, we'll get a different sample proportion. Since we're picking different samples with different probabilities, we're going to get different proportions with different probabilities. And our sample proportion is itself this random quantity that changes depending on which sample we take. So the natural question is, when is the sample proportion normally distributed? Right? We needed this for x bar. We're also going to need it for this p hat idea. So under what conditions do we have that p hat is normally distributed? And the answer is when the following conditions are met. So let me start by defining some variables. Let n be our sample size, as usual. P hat be the sample proportion. And P be the true population proportion. Then the sampling distribution of p hat is approximately normal when 1, the sample observations are independent, and 2, n times p is greater than 15, and n times 1 minus p is greater than 15. So this first condition is something we've seen before. We needed our different observations to be independent to get that normal distribution for x bar. In this case, we're working with p hat, same condition. This second condition looks new, right? This is a very sort of algebraic, do this calculation, and if it works, you're good, it's normal, and if it doesn't work, it's not normal. And this second thing, this second condition is called the success failure condition. And you might think, okay, so these are only two conditions. And remember, usually we needed, what did we need? We needed independence, we needed a large enough sample, and we needed there to not be a really large skew, right? Here we only have 2. We have that independence again, but rather than having large sample and lack of skew, we have this new thing, this n times p is greater than 15, or this n times 1 minus p is greater than 15. And what I'm going to show you in a second, I'm going to circle back, but I'm going to show you that this 2 is actually kind of equivalent to saying that the sample size is large enough and there isn't a skew, which is kind of cool, but I will get to that in a second. First, let me say that when these conditions, 1 and 2, are met, p hat is normally distributed with the following. The expected value of p hat, it is centered at the true population proportion. So just like how the expected value of x bar was the true population proportion of mu, we have that same thing here. It's centered at the truth, which is very good. And we have the standard deviation of p hat, otherwise known as the standard error of p hat, is equal to p times 1 minus p over n. So this is a little different. The standard error for a population proportion is a little different from what we've seen. It's not like the sample standard deviation divided by root n. It's actually this value right here. And here, p again is the true population proportion. Okay. I should mention though, of course, we don't know p. I mean, if we knew the true population proportion, why would we be doing any of this? We would just say, this is it, right? We wouldn't need to perform inference. And since we don't know p, we'll estimate the standard error of p hat, or otherwise known as the standard deviation of p hat, as exactly what you would expect it to be. Just plug in what our estimate is for it. It's our best guess, so we do the best that we can. So that's true, and I want to actually mention and check condition 2. So something that came up, I don't know, I kind of slipped it all by you, but notice here I've used the true population p for this condition. I didn't use p hat. And that's because technically this condition requires that this be true for the true population proportion. But again, this isn't something that we know, right? We would never really know this in any sort of application of this method. So instead, we check that second condition with this value, p hat. Okay, so if you don't know p, use p hat. So these are the conditions for inference, and this is the standard error associated with the population proportion. It's sort of new, right? We're looking now at a new tool, but all the same framework and all the different things that we need are all the same. Let me return to this success failure condition. So we checked some conditions, but what about sample size? Remember, we didn't check to see if our sample was greater than or equal to 30 in this case, right? And the reason we didn't do this is because the success failure condition covers this implicitly. The smallest sample size for which both NP is greater than or equal to 15 and N1 minus P is greater than or equal to 15. Smallest sample size for which these two things are true is 30. And I would encourage you see if you can figure out why. Don't worry, that doesn't mean I'm going to ask you this in the final. it's actually kind of a math proof to prove that when these two, the smallest n such that these two conditions could be satisfied is 30. So it's actually just sort of a consequence of the success failure condition, which I think is kind of cool, because instead of checking sample, we just check this one thing and it kind of gives us sample automatically. The other thing you might ask is, what about checking strongly skewed? Well, again, the success failure condition will ensure the lack of a strong skew. So again, this interesting new condition, this thing I've called the success failure condition, actually implicitly does the last two things that we usually check for when it comes to checking normality for inference, right? So I know maybe it kind of stinks that I'm introducing another condition for you to remember, but I think it's one, it's cool that it's kind of doing everything for you if you just check this thing. And two, unlike strong skew and sample size, this is a very explicit condition, right? It either is or it isn't. You can check it algebraically, and you don't have to do that sort of hand-wavy gray area that I've pushed you to do a lot this semester. So something kind of cool? I think so. So these are our conditions. If we can check them, then we have that P hat is normally distributed with this standard error centered at this value. And these are all the pieces that we might need to do inference. So without further ado, let's do some inference. We'll start with confidence intervals. Okay. So let's return to our Supreme Court example. Remember, they did a sample and they got 44% of people seemed to approve, and that was from a sample of 976 Americans. So, thus, what's our standard deviation of p hat, or the standard error? Well, since we don't know the true population proportion here, we're going to use our sample proportion to say that it's equal to this, to approximate it, which gives us around 0.016. So to get a 95% confidence interval, we do what we always do. The framework never changes. It's a point estimate plus or minus a critical value times the standard error, right? This is the same format for any confidence interval we've done this whole class, or will ever do in this whole class. And to get these different values, we'll just say, well, what's our point estimate? Our best guess at the population proportion is just going to be the proportion that we found in our sample, right? It's our best guess. There's no other reasonable best guess. So we'll just say that the point estimate is 0.44. The standard error, I gave you the formula, and we actually just calculated it literally 2 seconds ago. Not literally 2 seconds ago, figuratively 2 seconds ago. And our critical value is actually going to be the same thing it always is. So since our proportion, since our sample proportion is normally distributed, we have that we can use the normal distribution, which means we're going to use the normal critical value for our C. So this is the alpha over 2 critical value, which is equal to that norm dot S dot inverse of 0.05 over 2. Since we're doing a 95% confidence interval, the absolute value of that, which is equal around to 1.9599. Okay. So we have all of these values. Let's put them together. We have 0.44, our point estimate, plus or minus our critical value, times the standard error. And this will give 0.71. This is the same sort of confidence interval that we have done before. It should have the same interpretation, but just as a reminder, I'm going to write a sentence sort of interpreting what this means. We are 95% confident that the true proportion of Americans who approve of the job of the Supreme Court in June 2012 is between 0.409 and 0.471. Okay, so it has the same interpretation. We're talking about the population proportion, and we made a confidence interval that we hope captures the true population proportion, and we are 95% confident that this one does capture it, right? So any questions on this? No? Straightforward. This is just another confidence interval, just for something new. We're talking about a proportion now. The logical next thing, oh my goodness, it's hypothesis testing. So we have another example. Let's go ahead and write out. The candidate, Deborah Toohey, which, by the way, I stole this example from a book, and I have no idea if this is an actual candidate. So maybe somebody Google it for me and let me know. This person might be made up, but whether or not she is running for Congress. And her campaign manager claims she has more than 50% support from her district's electorate. So this is the claim of her campaign manager. A newspaper that wants to test this claim performs a simple random sample of 500 potential voters. And gets an estimate of p hat is equal to 0.52. So they They randomly sample 500 people in Deborah's district, and they asked, are you going to vote for Deborah, or do you support Deborah, or do you not? And they say yes or no, and they put all this data together, and they got 52% of them did support Deborah, or do plan on voting for Deborah. So let's perform a hypothesis test. The question is, does the true proportion, if we had every single person in your district, is the true proportion greater than 50%? And we would frame, our first step is we would frame this in terms of our null and our alternative hypothesis. So our null is that p is equal to 0.5, right? The true population proportion is equal to 0.5 versus it being greater than 0.5. And let's do this test at off of 0.01. Okay? So this is our first step, pretty straightforward. We just frame a research question. You all do very well on this on the homework. So I think we get this step at least. And I hope we get the second step, which is also very easy, which is just assume the null hypothesis. So we're going to say let p be equal to 0.5. We're going to proceed forward under the assumption that the true population proportion is equal to 0.5. Next, we'll do step 3, which is the hard step, find the p-value. The first step of this step, I guess sub-step, right, is to check your assumptions. The first, we'll note that this is a simple random sample of less than 10% of the population, right? So we have independence, independent. Next thing to do is to look at that thing that we just learned, the success failure condition. So NP is equal to, well, our N was 500, and by our null hypothesis, right, P is equal to 0.5. So this is 250, which is indeed greater than or equal to 15. We're good. Let's check the other one. It's equal to 500 times 1 minus 0.5, equal to 250, which again is greater than or equal to 15. All right, very nice. Success failure condition is satisfied. Therefore, P hat is approximately distributed, normal, centered at P with a standard deviation of the standard deviation of P hat, or the standard error. And we know that this value, the standard deviation of P hat, otherwise known as the standard error, is equal to this, which is just 0.5 times 1 minus 0.5 over 500, which is approximately, actually, gotta look this up. There was an error on my notes, so what I have on my notes is wrong. Let me say root of 0.5. This is going to be approximately 0.02236. Okay? So this is our standard error. What did we want to validate? We wanted to validate a one-sided upper hypothesis test, right? So this is an upper. One-sided hypothesis test. So what's our picture? We have this normal distribution. something like that. It is centered at our null value, which we said P was, and we have this other value that we observed. We observed 5.2. So what we want is for a one-sided upper, we want the probability of being at and above. Okay? So to do this, we calculate our z-score, which is just what it always is, x minus mu over sigma, which here is equal to our observed sample mean minus our null value over our standard error. Oop, that's not the right standard error, my bad. What did I say standard error was? 0.02236. Which, and again, I need to put this value in myself because I made a mistake on my notes. So 0.52 minus 0.5 divided by the square root. We're getting this to be 0.8944, around there. And to get, so that's the z-score here. To get this probability, which is going to be our p-value, since it's a one-sided test, we don't times by 2. This is just going to be the p-value. To get that, we do 1 minus our norm.s dot this function of 0.89443, comma 1, which all right, let me put it in my Excel 1 second, which is 1 minus norm dot s dot dist of 0.89443, which is going to be around 0.185546. Okay, so we found our p-value. The final step is to make your conclusion. So we'll note that alpha equal to 0.01 is actually less than 0.185546. So we fail to reject the null hypothesis. So we do not actually have enough evidence to refute, or I guess to, we do not have enough evidence to validate the claim that Deborah is doing better than everyone else, has more than 50% of the support. There is some ambiguity, and we really can't say anything based on the sample. Or at least we can't say anything about that particular set of hypotheses. All right? Any questions on this? Oh boy. Oh boy, this is the last topic. Don't cry. I think this next thing is actually really cool because it's very applicable. Like, there are a lot of research questions that ask about things like this, and this is how you can actually answer those research questions. I really hope one day you use at least one thing from my class, and it's gonna be like when you're 80. You're like, I did it. Let's talk about the difference in two proportions. Consider the following data. So I have this I'm going to show you, and I'll put this on as well. So let me first intro it, and then I'm gonna talk about what this data is actually saying. We are interested. I think this is a really cool example. We are interested in the approval of the 2010 Obamacare. law under two different question phrasings. So this is the question. So this was a survey in which respondents were asked this question. As you may know, by 2014, nearly all Americans will be required to have health insurance. People who do not buy health insurance will pay a penalty, while people who cannot afford it will receive financial help from the government. Do you approve or disapprove of this policy? So ultimately, the question that they ask is approve or disapprove. There's one of two options, right? And people respond, I approve, I disapprove of Obamacare. But something that's really cool is there are 2 points that they make about Obamacare. There's people who do not buy insurance will pay a penalty, and people who cannot afford it will receive financial help from the government. So there are these two things, and what they did is they asked this very same question to two different groups of people. And for one group, this first point was said first, and the second point was said second. So exactly how you see it, they were asked exactly this question. And for the second group, they swapped them. So they swapped what you see in this bracket here with what you see in this bracket here. So instead they asked, people who cannot afford will receive financial aid, while people who do not buy will receive a penalty, right? Do you see how there are two different questions here? And this is the responses that they got for these two groups. This first group, I'm just going to call it P1, is the group where where they talk about financial health as the second thing that they say. And the second group is the group where they talk about paying a penalty as the second thing that they say. So the question is, they're getting approve, disapprove, or whatever, but they're not actually asking a question about whether or not the American public approves. They're really asking a question of, does the rate of approval change if we ask the question slightly differently? Which I think I think that's so cool. That there's, the suggestion is that there's this implicit, how you frame the question really does affect how how somebody's opinion is going to be on it, even if the thing you say is really identical, right? They're portraying the exact same information. They're just literally swapping the order in which they make 2 points. So there are two different, this is like the first proportion and the second proportion. And there's two different sample sizes. They aren't actually equal. So this is the first sample. It was 771 people were asked. With 771 people were asked this first question, and 732 people were asked the second question, right? And then what you see here are the percentage of approval. So it looked like under this phrasing, 47% of people approved, and under the second phrasing, 34% of people approved, right? So it would appear, if we just looked at our sample, that the phrasing did make a difference. But the question is this evidence to believe that if we were to ask every single American the two different phrasing, would it make a difference for the whole population proportion difference, right? And that's what we're going to try to answer. And we have, oh my goodness, we have all the tools that we need. We can do it. So we want to know if the proportion of approval for one ordering is different than the proportion of approval for the other ordering. That is, we are trying to make inference on this difference. P1, the proportion associated with 1, and the proportion associated with 2. And I want to make the point, this is just like something we've done before. It is just like inference for non-paired data. We're looking at the difference of two means. Remember I made the point that really a proportion is, we can view it kind of like an average? Well, we're kind of doing the difference of two means here for non-paired data. That's kind of what this problem boils down to. So I'm going to do the first bit of inference for this, which is a confidence interval. So I'm going to teach you confidence interval, and maybe now would be a good time to mention I'm also teaching how to do a hypothesis test for this, which of course, is the natural other thing that we would do. But one, I'm doing it on the lecture video. And two, there's something about the doing hypothesis test for this that's kind of complicated. There's this sort of really nuanced complication that shows up whenever you do hypothesis testing for this sort of problem. And I'm still teaching it. I think it's a really important thing for everyone to know, but I decided that that I didn't have enough time to give you like enough practice and homework assignments on doing hypothesis tests with this for me to really feel comfortable to give it to you on your final. So the lecture video, which is posted right now, that won't be covered on your final, but it may be covered on your homework. So do still look at it. It's definitely an important topic, but I was worried it would be such a curveball and no one would get it on their finals. So just so you know, it's this material in this particular lecture that'll be everything on your final, up through the end of this lecture. Okay, so without further introduction, let's talk about 90% confidence interval for the difference of these two means. So if we want to perform a confidence interval, we need to check our assumptions. And just like when we checked assumptions for non-paired data, it is sufficient to do what we always do, check the assumptions, but check them for both P1 and P2, right? What we really want is here, let me say this. So we're making inference on P1 minus P2, right? So we're going to estimate it with the only thing we have, the difference of the sample proportions. And we want this value right here to be normally distributed. And what I'm telling you now is that you can just check that each of these are individually normally distributed. And if they are, their difference is also going to be normally distributed. And this was the same thing we covered whenever we did inference for non-paired data. Anyway, so we will check our assumptions. We'll do it one at a time. Let's start with P1. So P1 is indeed a simple random sample of less than 10% of the population. Our population is all Americans, right? So I think we had 700 something. I think that's definitely less than 10%. We will then check the success failure condition. Which is n times P1, which we don't know what P1 is, right? If we did, we wouldn't be doing this. So we will estimate it with n P1 hat, which is equal to 771 times 0.47. I don't know, here, I'm not pulling out these numbers out of nowhere. If you recall, this was N1, 771, and 0.47 was the first sample's proportion. So times 0.47, which is 362.37, which is indeed greater than or equal to 15. That one works. Then we have n times 1 minus P1, which we approximate with n times 1 minus P1 hat, which is 777 times 1 minus 0.47, is equal to 408.63, which is also greater than or equal to 15. Boom. So it looks like P1 hat is normally distributed. So that's good. Let's check it for P2 hat. This is a simple random sample of less than 10%. of population. So that one works. We have independence. And then next we have NP2, which again we approximate with NP2 hat, which is equal to 732 times 0.34, which comes out to 248.88, which is greater than or equal to 15. And then we do the same thing for N times 1 minus P2, and it follows the same way. Boom. Okay, so these are the conditions you need to check for this sort of confidence interval. We seem to have them all here, so we can say, since both p hat 1 and p hat 2 are normally distributed, p1 hat minus p2 hat is also normally distributed. Where it's centered, its expected value is exactly the population difference. So that's good. We're centered at what we want to be. And the standard deviation, p1 hat minus p2 hat, otherwise known as the standard error of their difference. So this is another nasty formula, but if you think about it, it's very similar to the standard error of non-paired difference, of difference of the means for non-paired data. It's that sort of sum of their individual standard errors. So this is the standard error for the first sample, and this is the standard error for the second sample. And I'm adding them and putting them all under the square root. Or rather, these are the variances for each samples. They're not the standard errors, my bad. Or the standard error squared, at least you can think about it that way. Okay, so that's this, and I'm gonna, let me be more precise. I don't know if I explicitly define these, which is N1 is equal to the sample size of the first group N2 equals sample size of the second. Okay, so we have all of our parts. Let's make our confidence interval. So confidence interval is always point estimate plus or minus C times the standard error. The point estimate here is P1 hat minus P2 hat, which if you go back to our data table is just 0.47, the proportion we got from the sample from the first group, and 0.34, the proportion we got from the sample from the second group. So we're gonna get a difference of 0.13. Our standard error is gonna be this monster, which we approximate with 0.47, 1 minus 0.47 over 771 plus 0.34, the sample proportion 1 minus 0.34 over 732. So we don't know the true values P1 and P2, but we can certainly predict them. We can make an estimate of them. And this is going to come down to about 0.025. Third thing we need is the critical value, which again, since we said P1 hat minus P2 hat is normally distributed, This is going to be the alpha over 2th quantile of the standard normal, which is this 0.1 over 2, which is around 1.65. Thus, this is our point estimate times our critical value, plus or minus our critical value times our standard error. And we will get a Converse interval of, right? So we are 95% confident that the true population difference, the true difference in the population proportions is in this interval. And I want you to notice something. Is 0 in this interval? No? Doesn't that mean that we're 90% confident that there is a difference? We're 90% confident that indeed changing the phrasing of this question really does make a difference with the population rate. So it seems the suspicion based on the sample is true that simple rearranging of ordering does actually make a difference in how people respond, even though the information is identical. Ah, my field is so cool. So, any questions on this? No? That was actually very nice. My second section, you always get through things so much faster than my first section. If there are no more questions on this, which I'll stick around if there are, then that is actually it for this lecture. You should check out the lecture video and join me for a game on Monday.